We are given this graph of f prime of x, and we are also told that f of 2 equals 0 on the original function, and we are asked to find various other parts or points on the original function. So we have a table set up here, so let's go ahead and enter that when x equals 2, f of x equals 0. And let's investigate what f of 5 would be. Okay, folks, the way we're going to get f of 5 is we're going to find the net change between x equals 2 and x equals 5. And whatever that net change is, we're going to add that to the y value at x equals 2, which is 0. Okay, how do we get net change in calculus? The way I remember this is that net change is the integral of the derivative. North Carolina is delightful. Net change is the integral of the derivative. So if we take the integral of f prime of x from x equals 2 to x equals 5, that would give us the net change. But folks, the problem is we don't have the function to take the antiderivative of. So what we're going to recognize is that this definite integral of this graph, f prime, this is the graph of f prime, the definite integral from x equals 2 to x equals 5 is the area under the curve. And we could get the area under the curve rather easily because they have this nice geometric figures here for us to take the area of. So here is where x equals 2, here's where x equals 5. If we take this area, there's two ways to do it. We can do 1/2 base times height, or we could just count boxes. So that's 3, 4.5, and we have to recognize that that is beneath the x-axis. So the area under the curve in this section from x equals 2 to x equals 5 is negative 4.5. So folks, we're simply going to add negative 4.5 to 0, and therefore f of 5 is going to be negative 4.5. Next, we are asked in number 21 to find f of 0. So here it is in the table. We're trying to find the value of the original f function when x equals 0. We don't know what it is. What we're going to do is find the net change by taking the area under the graph between x equals 2 and x equals 0, and then whatever that net change is, we're going to add it to 0. Okay, so here on our graph this is the f prime graph. Here's x equals 0, and here's x equals 2. So this area here is a half a box and a half a box. That is 1, and it is positive 1. Now, folks, very important. The only thing is that when you're going from x equals 2 to x equals 0, you're going right to left. We are not used to doing that in math. So instead of positive 1, we're going to flip the sign of whatever that original area is, and the net change then becomes negative 1. Therefore, on the original graph, f of 0 is going to equal negative 1. Next, in number 22, we're asked to find f of negative 3. I went ahead and placed it in the table. So what we can do is we could start now at x equals 0 because we have its f value. So I'm going to find the net change between x equals 0 and x equals negative 3. And whatever this net change is, we're going to add that to the value of negative 1. The net change can be determined by the area under this curve. So here we can't quite count boxes. So this is a base of 3 and a height of 2. 3 times 2 is 6. 1/2 of that is 3. And this is going to be negative area because it's underneath the curve. Now, folks, remember, the fact that we're going from x equals 0 to x equals negative 3 means we're going right to left. That's opposite to what we do. Therefore, we're going to change that to a positive 3. And when we add a positive 3 to a negative 1, we're going to get positive 2 for the value of f of negative 3. Next, we are given this graph of f prime of x, and we are told that a function is defined on a closed interval from negative 2 to 8, and that f of 2 on the original graph equals 1. Okay, A, does f, the original graph, have a relative minimum, maximum, or neither at x equals 6? We are reminded that this is the graph of f prime, and they're asking us what's happening on the original graph at x equals 6. Okay, it's important to remember, folks, that the y value on f prime is the same thing as the slope on f. Okay, so let's look at the y values around the point x equals 6 on the graph of the derivative. So here at 6, the y value of the derivative is 0. That means the slope on f is 0. To the left of x equals 6, we see that the the y value on f prime is positive. If you have a positive slope on f, that means the graph is increasing. Now let's look, let me rewrite this word slope. Now let's look to the right of x equals 6 on the f prime graph. We see that to the right of 6, f prime has a positive y value. The y value on f prime is the same as the slope of f. If the slope of f is positive, that means f has to be increasing. So here, folks, we have neither a relative minimum, relative maximum at x equals 6 on the original graph. Before we leave question A, let's talk about what the graph of f prime would have to look like if you have a relative extrema. And you see it right here at x equals 2 or x equals negative 1. Let's look at x equals 2. At x equals 2, the y value of f prime is 0, therefore the slope is going to be 0 on the f graph. To the left of x equals 2, you see that the y value is negative on the f prime graph. A negative y value on f prime means a negative slope on f, which means a decreasing function. To the right of x equals 2, you see that the y value on the f prime graph is positive. That means the slope on f is positive. That means you have an increasing function to the right of x equals 2. So you have to see the f prime change signs across a f prime value of 0 to have a relative extrema. Okay, let's now move on to question B, and they ask us about, are there any portions of this graph where f is concave down? Okay, whenever you see the word concavity, you should be thinking about the second derivative. So let's put the second derivative graph over here, and let's remind ourselves that the y value of the f double prime graph is the same as the slope on the f prime graph. So if you are looking for areas on f that are concave down, you're going to have a negative value for f double prime. That's where f is going to be concave down. If you have a negative value if the y value is negative on f double prime, then the slope is negative on the f prime graph. So where is the slope negative on the f prime graph? It's where f prime is decreasing. So it is these two portions of the f graph where it's going to be concave down. So when x equals negative 2 to x equals 0, that portion of f is going to be concave down. And from where x equals 4 to x equals 6. Why is it going to be concave down? Because if it's concave down, its second derivative is negative. If the y value of the second derivative is negative, then the slope on the f prime graph is negative. If the slope of the f prime graph is negative, then f prime must be decreasing. For part C, we are asked to find the limit as x approaches 2 of this expression. So if we plug in x equals 2 here, 6 times f of x, we're already told that f of 2 equals 1. So we're going to get 6 6 times 1 is 6, minus 6 is going to be 0 in the numerator, and when we plug in x equals 2 in the denominator, we're also going to get x equals 0. Therefore, this is L'Hopital friendly. So let's take the derivative of the numerator. It's going to be 6 times f prime of x minus 3. And the derivative of the denominator is going to be 2x minus 5. So now if we take the limit as x approaches 2, f prime of 2, right here, now we have the f prime graph to use. F prime of 2, the value is 0. So we're going to have negative 3 in the numerator, and if we plug in 2 for x in the denominator, we're going to get 4 minus 5 is negative 1. Therefore, our limit is going to equal 3. Next, in part D, we're asked to find the absolute minimum value of f, the original graph, on the closed interval between x equals negative 2 and x equals 8. So, folks, this is the graph of f prime. So the fact that f prime exists everywhere throughout that entire interval means that f is differentiable on this interval. So if it's differentiable, then f must be continuous. And the the extreme value theorem tells us that if you have a continuous graph that's differentiable, that the absolute maximum or minimum are going to be present either at the endpoints of your interval or at some place along the graph of f where the slope equals 0. So what we're going to do is we're going to investigate the f values at the endpoints and also here at the points where the f graph has a slope of 0, because we're going to go to the f prime graph and identify those points as negative 1, 2, and 6. Okay, so they were kind enough to give us in the beginning of the problem that f of 2 equals 1. So that's one of the places where f prime equals 0, so we don't have to get that f of. But we're going to go ahead now and we're going to add the endpoints, which are negative 2 and 8 for x values, and then we're going to add negative 1 because the derivative value is 0 there, and we're going to add 6 because the f prime value is 0 there as well. Okay, folks, what we're going to do is we have f of 2 equals 1. So we're going to start at f of 2 and we're going to move to these other spots in our table. So the first thing we're going to do is we're going to move from x equals 2 to x equals negative 1. We're going to get the net change. That's going to be the area under this curve. We're then going to apply the net change to the y value of 1 to get our f of negative 1. Now note, when we go from x equals 2 to x equals negative 1, we're going backwards. We're going from right to left. So whatever this area comes out to be, although it's technically negative, we're going to switch the sign and then add it to 1. Okay, I've gone ahead and computed the areas for sections 1, 2, and 3. The only areas that were a little bit challenging were sections 4 and 5. So to do this, we're going to take the area of this big rectangle and we're going to subtract the area of this semicircle. The semicircle has a radius of 2. So here's the math on that. We have the rectangle area is 4 times 2 or 8. The full circle, pi r squared, would be 4 pi. We only have half a circle is 2 pi. So the rectangle minus the semicircle is 8 minus 2 pi, and then these regions are symmetric. So we just take half of 8 minus 2 pi, or 4 minus pi for both of them. Okay, let's go ahead and enter 4 minus pi for the areas of those two sections, and they're both positive because they're above the x-axis. Okay, now we're going to go to our table. We're going to start at x equals 2 where we know the y value. We're going to go to x equals negative 1. We're going to get the net change using the area of the graph, and we're going to apply whatever that net change is to the value of 1. So here we go. We're at x equals 2. We're going to x equals negative 1. That means we're going to use area 2. Area 2 starts out as negative 3, but because we're moving from right to left, we're going to reverse that. So we're going to take that negative 3, we're going to change it to positive 3, and we're going to add that to the value of 1, and therefore the f of value when x equals negative 1 is going to be 4. Okay, next we're going to start out at x equals negative 1, where we know the y value is 4, and we're going to move from negative 1 to negative 2. That involves using area 1. We have areas of the section 1 as plus 1 because it's above the x-axis, but again, because we're moving right to left, because we're moving backwards, we're going to apply a negative 1 as our net change, and our f value is going to be 3. Next, we're moving from x equals 2 to x equals 6. So that's going to involve sections 3 and 4. They start out above the x-axis. We are moving left to right. That is normal in math. Therefore, we're not going to change the sign. We're going to keep them as is. So we're going to add plus 2 for section 3, and then we're going to add 4 minus pi for section 4. When we do that, we're going to get a f of 6 value of 7 minus pi. Finally, we're going to move from x equals 6 to x equals 8. We're going to add this final area. We're going to add 4 minus pi to 7 minus pi, and when we do that, we get 11 minus 2 pi. Okay, folks, we have all the y values on the potential candidate points, and we know that 2 pi is a little over 6. Pi is around a little over 3, therefore both of these values are going to be greater than 1. 4 is greater than 1, 3 is greater than 1. So right here at x equals 2, comma 1, that is our absolute minimum on this interval.